We were talking about compound interest last time, and we were looking at kind of what you might call big investments, lump sum sort of things. Those are great when you get the opportunity to do them, but many of us don't end up with large sums of cash we can just set aside and build interest. In those instances, more often than not, what you'll end up doing is kind of having like a small amount taken out of each of your paychecks or something along those lines, some kind of payment that you end up doing every month, every quarter, what have you, that goes into an account that then builds interest once you've made the deposits. That's the sort of thing that I have going on with a retirement account. Each of my paychecks does exactly that. There's a certain percentage that gets pulled out. When you do those sorts of things, that's what we're going to call an annuity. So that's what characterizes what we call annuities. There are different varieties of them that we'll see as we talk about the content in section 6.3. Like we do, notes file, Moodle, you get it. So an annuity is some sort of financial plan that's characterized by regular installment payments. So every month, every quarter, I mean, every year is an option in some cases. So much like we saw with compound interest in the last section, we're also going to talk about the future value of an annuity, what it's worth when we're done with everything. So in that instance, we take all the payments we put in, that's part of it. We're also going to take whatever interest is built up on those payments and interest building on itself. You get the idea from 6.2 stuff. So there's two main types of annuities that we're going to talk about for now in terms of these future value calculations. The first ones that we're going to take a look at are what we call ordinary annuities. So an ordinary annuity, you make your payment at the end of whatever particular payment / compounding period you're dealing with. So like at the end of the month or something along those lines. So in that instance, your future value formula looks like this. So we have S, and this is going to look a little more intricate than what we saw in section 6.2. I mean, we're moving forward. Hopefully that stands to reason. But we've got kind of a bigger quantity sitting here. So I'm not going to drag you through the algebra that ends up generating this. It's kind of an interesting exercise. You can take a look in the book if I remember right. Our authors develop it if you're curious. So the idea here is as follows. I know those are squared off brackets. I'm not doing anything with a matrix. Don't worry. That's just I like having different grouping symbols since I'm already using parentheses in here. Okay. So S is future value, just like it was before. R is the regular payment amount that we're making. You see 1 plus I, that should look familiar. So periodic interest rate, same calculation formula, take an annual rate, divide it by however many payment periods you have. Raised to the nth power, n being the number of payments that you end up making over the life of the annuity. This minus 1 is important. I is sitting at the bottom again. So we have another, as I was going to say, that periodic interest rate shows up twice in this instance. Okay, so that's our formula. Let's take a look at some examples here, but unfortunately, I'm kind of going to need the board to cover this because this is kind of a bulky calculation, so just a moment. I really don't like jump cuts, but it wasn't worth watching me erase all this stuff, right? So I'm taking a look at our examples here. So we're putting away $300 at the end of each quarter, it says. So we've got an example where our installment payment is $300. It says each quarter, so that means that's going to happen 4 times a year, so that's our M. Our annual interest rate, it says, is 4%. So the little r is 0.04, okay? Okay. So as is usual from what we saw last section, we need to get hold of I, we need to get hold of N. Now you can really see why we like working out these I and N values, because this formula with a bunch of R's and M's flying around in T, it gets pretty bulky. Okay, so I is going to look like 0.01 once we divide our annual rate by 4. I didn't specify the time frame here. It says 2 3/4 years, so that would be 2.75 as a decimal. So we have 4 payments per year times 2.75 years. I trust you to check the arithmetic for me here. That's going to be 11 total payments. Okay, So now we have our I, we have our N, we have our R. Those are all the variables on that in that future value formula, right? So I fill in R of 1 plus I is 1.01. Again, if you need to write out 1 plus 0.01, that's okay. Just short on board space, you know. Minus 1 over I, not 1 plus I. Now I want the I value, the 0.01 sitting by itself at the bottom. Okay. Now, if you're entering this into your calculator, I totally understand if you're doing things in easy stages. Like I said, I've been at this for longer than a lot of viewers will have been alive. So what I'll often do in this instance is I type it all in at once. The brackets, don't try that. Your calculator will probably think that's a matrix thing. What I would recommend that you do, enclose the top of that thing in parentheses, because most mistakes I see on this, if you've got the right formula identified, it comes down to kind of trying to enter too much into the calculator and missing something in the order of operations. All right, so I said parentheses around the top of that thing. Technically, in your calculator, you can actually get away with not doing parentheses on this if you go ahead and write it as 1.01, if number parentheses bother you. Anywho, so once we crank out all the arithmetic on that, we should get $3,470.05. Again, rounded to the nearest cent. It's not a nice clean thing. So that's one future value calculation taken care of. So there's a couple more examples I want to take a look at here. There's sort of a classic like investment strategy type problem. So you imagine a pair of twins. One of them starts putting money away for a little while and then stops. The other twin doesn't start putting any money away until his or her, their twin, quits. So you basically got a question of which strategy ends up working out better. Is it better to make some small investments early and then quit and then just let it sit, or just plugging away at it methodically if you don't get the opportunity? So let's take a look at those real quick. The magic of the jump cut. Anyway, let's take a look at twin 2. It feels sort of weird, but it's the kind of more, there's more investment going on in this instance, because according to the problem, our twin spends 36 years making payments. So everything is happening on an annual scale here. So I and R are the same. N is just the number of years we let it sit. So we have an I value of, I believe it's a 10% interest rate. So 0.10 converted to a decimal. N is 36, and we're given at this point $2,000 are being put away at the end of each year. That's how it says end. That's how we know it's an ordinary annuity. So now let's see how much our twin ends up socking away. We have R times this thing here. Again, 1 plus I is 1.10. If you didn't write the O, it's okay. To the 36th power, because that's our number of payments we're making, minus 1, all over 0.10. Again, if you're entering all this in at once, parentheses around the top of this thing, it really is important. It'll throw stuff off massively if you don't do that. So, all right, we crank out the arithmetic here. And after the 36 years are done, our intrepid investor has put away $598,253.61. Feels like a hefty chunk of change. Again, we're talking about 36 years worth of investment, but I mean, even with that, that's only $72,000 in total payments. So feels like a lot. That's a lot of interest that's built up, right? Like I said, letting investments sit for a long time is kind of a thing. All right, that's twin 1. Let's take a look at twin 2. I realize I actually said that backwards. We just did twin 2, and we want to look at twin 1. Blame it on my dislike of jump cuts. Anyway, so twin 1 is doing the same thing that twin 2 is doing. They just start earlier and then kind of let the investment sit. So they're not immediately pulling this out and buying a car with it or anything. So same interest rate, same number of payments, not same number of payments. This is obviously not the same thing as 36, right? There's only 8 of them being done. and then $2,000 payments. The payment size is the same. So we still got 2,000. I'll go ahead and do those parentheses from the get-go this time. So again, the only thing that's really changed in this formula as we work this out is the value of n. So we crank this out. Unsurprisingly, it's a smaller number, much smaller, in fact. I got $22,871.78. Now, again, unsurprisingly, this is lower than what our other twin has gotten on their money. The catch is they're not just immediately pulling this out and spending it. They're going to let it sit. So at this point, we kind of jump back to the last section. We apply the compound interest formula for the remaining 36 years. So running short on board space here, but the idea is, just I haven't put a box around this. Now we're going to treat this thing as a lump sum investment and then just let it sit for 36 years worth of building interest. And this comes back to figuring out which twin ended up having the smarter or better strategy. So I'm going to leave that part for you to take a look at in an assignment. So we're going to have another video coming up where we take a look at this formula in a slightly different direction.